Okay, so that's what we're going to look at. So the first question here, okay, the first question there, they're saying, consider the reversible reaction at equilibrium 392 degrees Celsius, where you have the reaction 2A, which is in gases, plus B, which is also in gases. It's producing, okay, so this is the reversible. So we have these two mass symbols. It's producing C, which is also in what? In gaseous state. Okay, and then from there, this is the reaction that we have been given. And then they're saying the partial pressures are found to be, for A, we have 6.7 atmospheres. For B, we have 10.1 atmospheres. For C, we have 3.60 atmospheres. So they're saying now evaluate Kp. Okay, evaluate Kp. So we know that Kp will just be given by the concentration of the product raised to its coefficient of moles. Okay, so we can say N, and then divided by the reactant. So let's say I have Q as my reactant. I think let me just use the letters that are here, right? So let me say this is C. So the concentration of, the pressure of C raised to its coefficient moles divided by the concentration of A raised to its coefficient moles, okay, and then divided by the partial pressure of B raised to its coefficient moles. So we can say this is T. Okay, so this T, M, and N, we can get them from the chemical equation there. Okay, so this number here in front is the one that will be where the M is there, because this is for the A. And then for the B, we see that we have 1 here. So it means this T here is going to be 1. And then for the C, we also have 1. So it means this N here is going to be what? 1. Okay, so to calculate Kp now, we are just going to replace those quantities with their values. So the first one is the C. So the C is given as 3.6. Okay, and then we are going to raise this to power 1. We're going to divide this by the pressure of air, which is 6.70 raised to power 2, and then the pressure of B, which is what, 10. Okay, 10.1 raised to its coefficient moles, which is 1. Okay, so this is what we have. And then from there, we just have to punch the value into the calculator. Okay, so let's punch those values into the calculator and see what value we're going to get. Okay, where's my calculator here? Okay, so on top there, I have 3.60, and then I'm dividing this by 6.70 raised to power 2 multiplied by 10.1 raised to power 1. Okay, so this is what we are multiplying there. So according to my calculator, I'm getting this as my answer. I'm getting 7.4 multiplied by 10 to the power minus 3. Okay, so this here will be the value of the Kp. So you can go back on your answers, you check for it. We see that it will be on A there. Okay, so the A there is the answer. So any questions there before we go to question 12? Okay, no question. Let's move to question 12 then. So question 12, we have we are calculating the equilibrium concentrations. Okay, so it means we have to use the ice table there. So the question says, okay, consider the reaction N, let me be writing the reaction, N2 in gases plus O2 also in gases, and then this is producing, okay, 2NO, which is also a gas. Okay, so they're saying the Kc value, okay, the Kc value, which is the equilibrium constant in terms of the concentrations, is equals to 0.1, okay, at 2000 degrees Celsius. Okay, starting with the initial concentrations of 0.04 for nitrogen and 0.04 for what? Oxygen. Calculate the equilibrium constant. Okay, so let's write the reaction here. So I'm going to write nitrogen plus oxygen here, and then these are producing, okay, NO like that. which has a 2, of course, here. So what we are going to do here is come up with the ice table. So we're going to say initial concentrations, the change, okay, and then the equilibrium there. So the initial concentration of N2 is just 0.04. The initial concentration of oxygen is just 0.04. Okay, the initial concentration of the NO there is just 0. So what is the change now? Okay, so this 0.04 is going to reduce by X. Even this 0.04 is going to reduce by X. And then this 2NO is going to increase by 2. So we're going to write 2X there. Okay, and then from there we can calculate the equilibrium concentrations there. So we're going to say equilibrium concentration will just be 0.04 minus this X. Even here 0.04 minus the X. And then here it's going to be 0 plus 2X to just be 2X, right? So this is what we have there. Okay, and then from there now we can calculate the equilibrium concentrations using the K value here. So we have to know that the Kc is equals to, okay, the concentration of the product. In this case, the concentration of the product is just NO. And then we say this to the power 2 divided by the concentration of the reactants. Okay, the concentration of the reactants is the concentration of nitrogen gas, okay, and multiplied by the concentration of oxygen gas. So we replace this concentration here and these concentrations here with the concentrations at equilibrium, which are just these to my 0.04 minus X, like that. Okay, so let's create some space here on top so that we can show the calculations. Okay, so we're going to say Kc value is just 0.0, it's just 0.1. Okay, 0.1 is equals to the concentration of NO, which is 2X to the power 2, divided by the concentration of nitrogen, which is in this case is that guy there. Okay, so that guy there is just 0.04. Okay, even the other guy, oh, I've forgotten the X there. So 0.04 minus X, like this. And then the other one is also 0.04 minus X. Okay, so this is what we have. So from here, we can say that what we have here is just 2X squared divided by, this here is the same thing. So we can write it as 0.04 minus X, and then what? Squared. Okay, so our goal there is to find the value of X. Okay, so what do we do from there? We just cross multiply, and then after cross multiply, we try to find the value of X. So we are going to get the quadratic equation here. Okay, so we have that 0.1 is equals to this. So when we cross multiply, what are we going to get? Okay, cross multiply, we're going to get 4x squared. And then on the other side, okay, we are going to expand what we have there. Okay, we're going to expand what we have there. So the first one is what? Is okay, so this is minus x, like that. Okay, so we're going to say 0.04 multiplied by 0.04. What are we going to get? Okay, we are going to get 0.00016, like that. Okay, then 0.04 minus this x, it will be 0.04 multiplied by minus x, it will be the same 0.04 x, and then minus x multiplied by 0.04, it will be 0.04x, and then minus x multiplied by minus x. What are we going to get there? Okay, minus x multiplied by minus x, we are going to get plus, this should be plus x squared, like that. Okay, so this is the quadratic equation that we have. Okay, so let's try to solve it. So we are going to say 4x squared, and then we take all these here to the left hand side, so it will be minus x squared. And then when I take this and this, which is a minus, so when I add them there, I get minus 0.08x. So I take them to the other side, so it will be plus 0.08x. And then I'm remaining with the 0.0016. Okay, and yeah, so that's what I'm remaining with. So I'm going to say minus 0.0016. Okay, so this is what we have. So from there, what are we going to do? Okay, what are we going to do? We are going to subtract. So here we're going to have 3x squared minus 0.08x minus 0.0016. This is equals to, I've forgotten 10 here. So it should be another 0 there. This is equals to 0. And then we see that this is just a quadratic equation. So we use the quadratic formula because we can't find any factors there. So when we use the quadratic formula there, it will be my A will be equals to 3. My B will be equals to, this one here should change the sign, right? Because we took it to the other side. So I don't know why it's still negative. So it should change. So the B is 0.08. And then the C is equals to minus 0.00016. Okay, so from there, we'll just use the quadratic formula. You know how to use the quadratic formula, right? Okay, so the quadratic formula will be equals to what? Okay, so the quadratic formula is just x is equals to minus b plus or minus the square root of b squared minus 4a. Then we divide this by 2a. Okay, so I'm not going to show the whole process here. Okay, I'm not going to show the process, but when you solve for x here, you are going to get x is equals to, okay, you're going to get two numbers. You're going to get the negative one and the positive one. So you only consider the positive one. So the positive one that you're going to get will just be 0.00546. Okay, so it means this here is how much of the concentration these initial concentrations are reduced by. Okay, they were reduced by this much, the initial concentrations. So now going back to our questions, our question, they said they want us to find what? Okay, in our question they said find the equilibrium concentration of NO. Okay, so remember the equilibrium concentration of NO was 2x. So it means we have to multiply that x by these 2. So it will be 2 multiplied by 0.00546. We multiply this, okay, what are we going to get? Right, so my calculator is saying 0.0109, and this is the concentration, so it's molar. So we can actually round it off. Okay, so when we round it off, we get 0.011 molar. So this molar here is the same as the moles per liter. Okay, so you go back now on your answers. You try to check if you have this value here. Okay, so we can see it's only C there. So C there, that is the answer there. So any questions there? Okay, I'll move to the next one then. So the next one, we have uh, this question here. They're saying, what is the PO and the concentration of hydrogen ions of 0.01 molar acetic acid that has undergone 3% ionization? Okay, so we need to know the formula for ionization. Okay, so percentage of the ionization, okay, the percentage of ionization is equals to the hydrogen ions that will be present at equilibrium, okay, divided by the concentration of the acid initially. Okay, so in this case, we are considering acetic acid, and then we multiply by 100. So this is the formula for ionization, for percent ionization. So here we've been given the percent ionization. So we can use it to find the concentration, first of all, of the H plus. And then once we have the concentration of H plus, we can find the pH. And then from the pH, we can find the pOH here. Okay, so we are going to say now, okay, we're going to say this hydrogen concentration, H plus, is just equals to the percent of ionization, okay, the percent of ionization multiplied by the concentration of the acid initially, okay, or the initial concentration of the acid. So here the percent is 3%, which is 3 over 100, multiplied by the concentration of this acid initially. So the concentration there is just 0.01. Okay, so let's now punch this into the calculator. Okay, so when I punch this into the calculator, what am I getting? Okay, I'm getting this as my concentration of the hydrogen ions. I'm getting 3.0 multiplied by 10 to the power minus 4 molar. So this is what we get as the concentration of the what? The hydrogens ion. So once we have the concentration of the hydrogen ions now, it means we can find the pH, and then from the pH we can find the pOH. Okay, so we're going to say pH is equals to minus log, okay, minus log of the concentration of the H plus. So the H plus, its concentration is 3.0 multiplied by 10, the power minus 4, like that. Okay, so when you do minus log of this, you should be able to get the answer there. So what else am I getting on my calculator? Okay, so when I do minus log of 3.0 multiplied by 10 uh, to the power minus 4, I'm getting approximately 3.52 as my pH. Okay, so to find the pOH, we know that pH plus pOH just equals to 14. So it means my pOH will just be equals to 14 minus the pH, which is 3.52. So this, when I subtract, I'm getting what as my pH? Okay, as my pOH, I'm getting 10.48. Okay, so this here is my pOH. All right, so any questions there? All right, we go to the next one. So the next one here, they're saying, which of the following compounds is considered a base in Arrhenius, okay, Bronsted, and Lewis acid theory? Okay, so you have to know the definition of a base in all those three theories, okay? So according to Arrhenius, okay, according to Arrhenius, he said a base, okay, is a substance that produces OH ions when it is dissolved in what? In water. Okay, OH ions. That is according to Arrhenius. And then according to Bronsted, okay, Bronsted said uh, a base should be a proton acceptor. Okay, should be a proton acceptor. And then according to the Lewis, okay, the Lewis theory says that a base, okay, uh, a base it's an electron donor. Okay. Okay, so it says the base is an electron donor. So we just have to look for a substance there on the number, on the four options given that can do all this here. Okay, so we start with maybe water there. So water can donate these ions, right? Okay, but it's not, it can also accept this, okay, but it cannot be an electron donor. Okay, same with this boron hydride here. Okay, this boron hydride cannot donate the OH ions. Okay, it does not produce these ions, so it can't be considered even the water. What about the ammonia solution? So ammonia solution is NH3. So this NH3 can never donate OH ions. Okay, so we cancel the ammonia. So we just remain with sodium hydroxide. So sodium hydroxide, okay, we can see that it can donate the OH minus ions, okay, and then it can also accept a proton, okay, and it can also donate what? It can also donate electrons, okay. So the one that satisfies all the definitions here is just the sodium hydroxide. So you pick sodium hydroxide there. Okay.
So I didn't get question 14 because my network was tripping. So I had to join the meeting again.
Oh, okay. So I was saying here we are looking for a compound, okay, that satisfies the three definitions of a base. So the first one is the Arrhenius definition. So according to the Arrhenius definition, they said a base is a substance that produces OH ions when it dissolved in water. Okay, and then according to Bronsted here, said a base is a proton acceptor, so meaning it accepts hydrogen ions like that. Okay, and then according to Lewis, he said a base is an electron donor. Okay, so it donates electrons like that. So of these four options that we've been given here, only the sodium hydroxide satisfies all the three definitions. Why? Because this sodium hydroxide here can donate one, the OH ions, okay? And once it donates this, the OH ions, these OH ions here can go and accept the hydrogen ions, okay, to form water. So this check, and then even this one here, electron donor. Okay, the sodium hydroxide can be able to donate the electrons uh, to the acid that it is reacting with. Okay, so only this sodium hydroxide here satisfies these three conditions. This one here does not, the water does not, even the boron anhydride does not. Okay, so is that okay now?
Yes, sir.
All right, let's look at question 15. So question 15, they are saying ti tri which titrimetric, okay, which titrimetric method uses the areochrome black tea, okay, which is also known as the EBT as an indicator. Okay, so whenever you hear EBT, okay, what should be coming to your mind is a complex or metric titrations. Okay, so that's where the EBT is involved. So here on your options, you have to cancel this volumetric, just remain with the the complex or metric titration. Okay, so since here we are dealing with EBT, okay, it means that complexo uh, metric titration, okay, should involve the EDTA, okay, because here we have EBT, which is the areochrome black tea. It means it should involve the EDT there. Okay, so the correct answer here you should pick is C. Right, so if it involved the cyanide, we would have picked the first one here. But here it involves the EBT, so we get this one here. Okay, so this one is you just have to like memorize it. Okay, so memorize this one. Okay, and then the next question we have what? We have this molecule here. So they're saying the relationship between the following two structures is, okay, so we have this one here, we can call it structure A. This one here, we can call it structure B. Okay, so when we look at these structures there, okay, we can see that they are almost similar. Okay, they are only differing at this chirocarbon here, this chirocarbon. Okay, so on the A there, we have the OH on the right, the H on the left, and then on the B, we have the OH on the left, the H on the right. Okay, so it means these structures here are just differing at one chiral center. Okay, so if you have structures that differ at one chiral center or even more chiral centers, we call those structures as what? Diastromers. Okay, and then these enantiomers are just structures that are not uh, superimposable on each other. Okay, for example, if you get your left hand, okay, and then you try to put your right hand on top there, they won't align like the fingers on top won't hide the fingers below. There will be that differentiation. Okay, so enantiomers are those molecules that are not superimposable on each other. And then when you have two molecules, okay, that differ at one chiral center or more chiral centers, we call that molecule or those structures as what? Diastromers. So here the best answer should be B. All right. And then number 18, we have this molecule to name. Okay, we have this molecule to name. So let me redraw it here. Okay, and then we have a solid wedge like that goes to the chlorine. I also have a dashed wedge that goes to the hydrogen, and then I have CH3. Okay, here I have a solid wedge that is going to the hydrogen, as you can see, and then a dashed one which is going to the bromine, and then I have this one which is going to the CH3. Okay, so to name this, we first have to identify the longest carbon chain. Okay, so the longest carbon chain can be 1, 2, 3, and then 4. Okay, it can also be, I start from here, 1, 2, 3, and then 4. Okay, so which one do you choose? which side do you choose to start your counting with? Okay, you go for the side that has uh, the highest priority. Okay, so here I can see CH3, CH3, hydrogen, hydrogen. Okay, and then we have now the boron and the what? The chlorine there. So which one here has higher priority? Okay, which one comes first between the boron and the chlorine there? Okay, we see that the one that will come first is the boron here. Why? Because it has a higher atomic number than what? Than the chlorine. So it means our counting will start from here and then it's going like that. Okay, so we're going to get the counting in yellow there. All right, so that's how we can decide which side to start with. Okay, so we're going to get that numbering there. Okay, so in your answers there, I can see the S and R configuration. Okay, so it means we have to find the configuration at this carbon and also the concentration, the configuration at this carbon. Okay, so we said that if you have a chiral carbon here attached to 4 different atoms, okay, the first rule is that your hydrogen, okay, should always be in the back. So it should be on the dash wedge like that. Okay, if it's not on the dashed wedge, then after finding your configuration, you have to take the opposite. Okay, and then we have to group these are 4 elements that are directly attached to this carbon by their atomic mass. Okay, so we get the one with uh, the largest atomic mass as our first priority, and then just like that. Okay, so when I come at this first carbon here, the carbon 2, okay, what will be the configuration there? Will it be S or will it be R? Okay, so this one here, it's grouped to the hydrogen on the solid wedge, the bromine on the dashed wedge, the methyl there, and then I have this whole group here. Okay, so let's assign the priorities to these groups. Okay, so the first one here, we are going to consider bromine. Bromine will be the one with the highest atomic number. So it will be 1. And then I have this carbon here, which is connected to 3 hydrogens. Then I have this carbon here, which is connected to to a carbon and a chlorine. So it means this one is heavier. So this one is going to become our 2. That one is going to become our 3. And then this is going to become our what? 4. So it means when getting the configuration, okay, we're going to go from 1 to 2 to 3. Okay, so when we go in the counterclockwise direction, we say that is the what? S configuration, right? Okay, and then you look at where your hydrogen is. So the hydrogen here is on the solid wedge. So it means we have to reverse our configuration. Okay, so this will be R. So the configuration at this C will just be what? R like that. Okay, so that's how we can find it. And then let's consider the 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 carbon 3 there. Okay, what configuration is it going to have? So we've said this one here is the R. What about this one? So this one is attached to chlorine, hydrogen, methyl, and this whole group here. So which one will be what? Okay, the one which will be number 1 is the chlorine here. So we're going to say number 1. Number 2 is going to be this carbon here. Okay, because it's attached to the bromine here. And then this is going to be number 3. The hydrogen is going to be number 1. So it means our configuration here will be from number 1 to number 2 to number 3 like that. So we are moving in the what? Counterclockwise direction there. So it means the configuration at this carbon will just be what? S. Okay, the configuration there will just be S. All right, so here we can't reverse it because the carbon there, I mean the hydrogen there is already in the back. So we just get the same way it is. Okay, so let's remove this and say this is what? S. And then once we find this, we can now name them. Okay, so it means this is my carbon 1, carbon 2, carbon 3, carbon 4. So at carbon 2 here, I have a substrate, which is what? Bromine. So that will be 2 bromo. Okay, that will be 2 bromo. And then at 3, I have a substrate, which is what? Chlorine. So that will be 3 chloro. Okay, and then the parent name here will be what? We have 1, 2, 3, 4, 4 carbons. So that's easy, butane. Okay, and then we are going now to add the R and the S configuration. So at these two here, we can see that it's 2R, and then comma. At this 3 here, it will just be 3s. Okay, so this is the name now. So you go on your answers, you check, we can see that it will be D there. Okay, so D is going to satisfy our desires there. So we pick D as the best answer. All right, let's look at another question, which is question 19. Okay, so question 19, they're saying what? They're saying in saturated hydrocarbons, carbon atoms are bonded to each other by, okay? So by saturated, we mean it has no uh there's no double bonds, okay? It has no triple bonds. So no double bonds, and again no triple bond. Okay, so it means the bonds in this hydrocarbon will just be one to one, okay, just be single bond. So carbon single bonded to carbon, just like that. Then you have the rest of them as hydrogen, since it's a hydrocarbon, okay, just like that. So what does this mean? What are these bonds here called? The ones that are single like that, okay, they're just called the single covalent bonds, okay. So we are going to go on our answers, then we are going to pick C. All right, so that is question number 19. Okay. And then question number 20. Question number 20, what do we have now? Okay, so we have a series of reaction here. We have to identify the processes at each change. Okay, so the first one is when I have CH3, and then CH3, and then from there, they said I've changed to CH3, CH2, Cl. So we can see here that one hydrogen here has been replaced by what? A chlorine. So what do we call that? Okay, we call that as a free radical substitution. Okay, free radical substitution. And then from there, I have this C3C to Cl, which is being converted to CH3, CH2, and then this chlorine here has been replaced by OH. Okay, so what do we call this type of substitution? Okay, we are going to say this is a nucleophilic. Okay, nucleophilic substitution. Okay, why? Because the hydroxide ions, okay, I've replaced the chlorine ions here. So this is nucleophilic. And then from there we have this one. Okay, we have this CH3, CH2, OH, okay, being converted to an ethene here, like that. Okay, so this is ethene here. So by what process do we convert that to an ethene? Okay, this process here is called the elimination. Okay, it's called the elimination because we just eliminate this OH here. Okay, once we eliminate this OH, this here will just be called the is it addition or no. This is elimination reaction. Okay, so elimination. On our answers, do you see any elimination there? Okay, free radical. Okay, so from here to there, what's the process there? The process there is supposed to be elimination because we've removed this OH. We can't see it anymore in this reaction. Okay, we've also removed a carbon there, so that we remain with CH2, CH2. Okay, so we are going to call that as the elimination reaction, which means that compound there has undergone dehydration, okay, to form ethene. And then the last one, okay, so let me write elimination here first of all. And then the last one is this ethene. Okay, I'll write it here. This ethene here changes to CH3, CH2, okay, and then I have bromine. So what has happened there? Okay, what has happened there? what has happened there is uh, electro, electro, electrophilic addition. Okay, what has happened there is electrophilic addition. So why is it electrophilic addition? Okay, it is electrophilic addition because on this double bond here, you can see this double bond, right? We have added a bromine like that. Okay, we have added a bromine to this double bond there. So that is electrophilic addition. So now we ask ourselves which one here is not, or which one is involved according to what we have explained. The free radical is involved, so we're going to mark it here. The nucleophilic addition, we're going to mark it. Okay, and then this is nucleophilic substitution. We are going to mark it as well. So the one that is involved, that is not involved here is this one here. The electrophilic what? Addition is not involved. Okay, since in this mechanism, uh, like the nucleophilic substitution, okay, it typically applies to maybe you have aromatic compounds, okay, and not alkanes or alkenes as we can see in this formula. So it will apply to the compounds that are in this form, something like that, okay, and then you have attack like that, something like that. All right, so this is the last question there. So any questions? Any questions?
No questions.
All right, I think I'll end here. So who also finished a the chemistry 1000 section A because we didn't finish. So I'll also create a video on that so that next week we look at section C on both papers. All right, so have a nice day.
All right, same to you, sir.